Welcome, beginner game developers. Today, we're diving into advanced state machines, a fundamental tool for managing complex behaviors in your games. We'll make the class abstract and define virtual methods: enter state, update state, and exit state. These methods will be overridden by our concrete states. This tutorial will cover a theoretical explanation, a practical demonstration in Unity and C#, and thorough testing of our implementation. At its core, a state machine is a behavioral model with a finite number of states and defined transitions between them. Key components include states, which represent a specific behavior like idle or jumping, and transitions, which are the rules governing how we move from one state to another. The state pattern offers an object-oriented approach, resulting in cleaner code, easier maintenance, and enhanced extensibility for your game systems. We'll briefly touch upon finite state machines, or FSMs, and hierarchical state machines, HSMs, understanding their fundamental differences in applications. Let's begin by creating a new Unity project. We'll name it State Machine Tutorial to keep things clear and organized. Next, we'll establish a logical folder structure within our project. This includes scripts, states, and characters to maintain order as our project grows. For our character, we'll use a simple 3D cube. This allows us to focus on the state machine logic without getting sidetracked by complex models. We'll then add a character controller component to our cube. This component provides essential physics and collision handling for character movement. Finally, we'll create an animator controller. Even without animations yet, this sets up the necessary structure for future animation integration. Now, let's create our base state class in Visual Studio. This abstract class will serve as the blueprint for all specific character states. We'll make the class abstract and define virtual methods: enter state, update state, and exit state. These methods will be overridden by our concrete states. Crucially, we'll include references to the character controller and animator components, allowing states to interact directly with our character. Next, we'll create concrete state classes: idle state, walk state, and jump state. Each will inherit from our base state class. For idle state, we'll override enter state to play the idle animation and update state to check for movement input, transitioning to walk state if detected. In walk state, we'll set the walk animation and implement basic character movement using character controller, move. We'll also check for jump input. For jump state, we'll trigger the jump animation and apply upward force. Upon landing, the character will transition back to idle state or walk state. Now, let's create our state machine controller script. This central component will manage the current state and orchestrate all state transitions. It will include a public property for the current state and a crucial change state method to facilitate switching between different behaviors. Within change state, we'll call exit state on the current state, update current state to the new state, and then call enter state on the new state. The initialize method will set up the starting state, and update will continuously call current state.update state to process current behavior. Now, we'll create a character controller script and attach it to our character in Unity. This script will be the bridge between our character and the state machine. Inside this script, we'll add references to the character controller, animator, and our state machine instance. We'll also create instances of our concrete states: idle state, walk state, and jump state within this script. In the start method, we'll initialize the state machine with our default idle state, setting the character's initial behavior. The update method will then call state machine.currentState.update state to ensure continuous state processing. Finally, we'll implement input handling using input.getAxis and trigger state transitions via state machine to change state based on player actions. Now, let's test our state machine. Run the game and observe the character's behavior as you provide input. Demonstrate transitions between idle state, walk state, and jump state by moving the character and pressing the jump key. Add debug logs in each state's enter state and exit state methods to confirm transitions are occurring as expected in the console. Tweak movement parameters like speed and jump force in Unity's inspector to fine-tune the character's feel and responsiveness. For best practices, keep your states focused and specific, avoiding overly complex logic within a single state. Use clear and intuitive naming for your states and transitions to enhance readability and maintainability for yourself and your team. If a state becomes too complex, consider breaking it down into smaller, more manageable substates to maintain clarity and organization. Always test each state individually before integrating them into the larger state machine to isolate and resolve issues efficiently. For advanced animation control, explore Unity's state machine behaviors, which allow you to execute code directly within animator states. In summary, state machines are indispensable for creating dynamic and responsive game characters and systems. Experiment with different states and transitions to truly master this powerful design pattern in your game development journey. Consider exploring hierarchical state machines and event-driven state machines for even more sophisticated game logic. Thank you for watching. If you found this tutorial helpful, please like, subscribe, and leave your questions or comments below.